However, you might ask yourself a slightly different question. You might say, what is the probability of a man being left-handed? It's a perfectly interesting question to ask. I'm using left-handed and male because you've all got a kind of, hopefully, got a kind of image in your mind. I don't need to go on and on and on about what it is to be male. I don't need to have a massive discussion of X chromosomes. I just say, oh, you know. But these two categories could be anything. This could be high blood pressure, and this could be will have a heart attack. This could be male. This could be suffers from depression. The reason I'm talking about this is that this is a simultaneous course with a level 8 course in health informatics, and the examples that those guys use are all medical cases. So this might be takes aspirin, and this one might be has high blood pressure. And of course the intersection is both of those. What's the probability of a man being left-handed? So I'll go back to male and female, left-handed and right-handed, because it's easy to understand and you don't have that load of thinking, what was the aspirin thing again? You might ask, what is the probability of a left-hander being female? Actually, I'll change that. I'll change it back to male. Not.
You just said the same thing then.
This is the probability of a man being left-handed. This is the probability of a left-hander being a male. So you can say, people walk in, and there's boys and girls walking in. And because I'm only interested in the men, if the girls walk in, I'm not interested. And I'll say, right, I'm just looking at the men, and I'm going to see how many of you guys are left-handed. And it might be different for the women. The men and the women might have different probabilities. But I'm using this because it's dead easy to think about. This one is different. This is, I'm sure you'll know that on lecture theatres, left-handers have difficulty with the seats. So left-handers tend to sit at a special desk that's got the writing pad on the right side, the left side, the right side for us. So I might say, oh, look at all these left-handers here. Seem to be a lot of women there. Or maybe there's a proportion of men. See, these are very different questions with a different answer. Let's just imagine it's independent. Let's just imagine that left-handedness is independent of gender, which I don't really know, but I think it is. So the probability of a man being left-handed is about 10%. The probability of a left-hander being male is about half, because about half of us are male and half of us are female. When I say us, I mean left-handers. These are different questions, and I'm glad you said that because it means I've got to be very clear. So let's have a look at this. I'll write this one as the probability of being left-handed, L, new notation, vertical line which means given, M. That is the probability of being, you read it like this, left-handed, given they are male. Probability of being left-handed, given male. This one is the probability, sometimes I'll just write P, probability of a left-hander. You see, you've got to turn it around because the way English is constructed, of a left-hander being a probability of male given that they're left-handed. You see, it's a different way. That's LM and that's ML. I've swapped it around. So how do we handle that? This has caused more confusion. This issue of confusing L given M and M given L has caused more confusion than every other statistical issue combined. possibly confidence intervals might be rivaling it, but hey-ho. So how do we work out this? Well, let's just think about this. Let's just try and label this. Let's look at the first one. Probability of being left-handed given that you're male. Well, I could prove this, but I won't. The probability of left-handed given that you're male is equal to this. It's the probability of L intersect M, which is this one here, divided by the probability of being male. So it's this area here divided by the area of that whole circle there. Okay, this is called conditional probability.
Didn't we say that the intersect was right-handed before, or are we getting rid of that idea?
The intersect is left-handed because you're in the L circle.
Well, before that,
You labelled it right-handed
you labelled
though
it
before.
right-handed before.
Did I?
Yeah.
Yes, you did.
Say that again.
The intersect on the last, you made it
Now we
right-handed.
drew it before.
Oh, RH is my initials.
Ah, okay.
Oh dear. Yes, he's absolutely right. I put RH because that's me. I'm Robin Hankin. I'm RH. And you thought it was RH being right-handed.
And the B circle is just left-handers.
Huh?
The B circle is just
Yes, that's right.
Okay.
That's right. Yes, that's me. Because I'm left-handed and male. I'll demonstrate I'm left-handed.
Thanks for clearing that up.
Never occurred to me.
For my husband's name, EA in it, and I'm like,
Gotcha.
Okay. I'm going to rewrite that. Maybe I'll drop left and right-handedness for a while.
No, that makes sense. I was confused with the R.
Oh. Probability of A given B equals probability of A intersect B over the probability of B. All I'm doing is relabeling L's and M's and A's and B's. Which incidentally is why I'm doing this, because it's possible to rename those circles and rename those I should put my universal set there. It's possible to rename these circles with anything. Let's just let that stand for a moment, and I'll write down the probability of B given A. All I've done, and this is a formal operation, is swap the identities of B and A. When I write this squiggle with a sort of cornery bit at the top, I'm going to write this squiggle with a sort of vertical bit and two sort of lumps on the right. And where I've written this squiggle with a sort of vertical bit and two lumps on the right, I'm instead going to write a squiggle with a cornery bit at the top. That's just a formal transformation of letters. All I'm doing is having a slightly different notation. You can see all I've done is transpose B and A. I've just swapped those over. And now the clever bit comes. The clever bit is this. Well, it's half the clever bit. Is that obvious? Yeah, of course it is. If it's in both, it's in both. So I can rewrite this one. Probability of A given B equals probability, I'm just writing everything, A intersect B over probability of B. And the probability of B given A is the probability of A intersect B over probability of A. You'll notice that all I've done to go from this blackboard to this one is to swap that A and B round, because it was originally B intersect A and now it's A intersect B, but I'm using this rule here. In fact, I'm not even using all of that. I'm not even using the identity of the sets. I'm using the identity of the probability of that set, and it could be a different set. I'm just using the fact that it's the same probability. So it's quite a weak statement. Okay. So probability of A intersect B equals probability of B probability of A intersect B equals probability of B given A, probability of A. All I've got is two expressions, one from the top, one from the second, one from here, for probability of A intersect B. Going too fast? Now what I'm going to do is I want an expression for probability of A given B. So from these equations here, probability of A given B equals the probability of B given A, probability of A over probability of B. This is known as Bayes' theorem. That is what it is called in English-speaking countries. Anybody who calls it this will fail. Yes, that is correct British English. No, this is foreign colonial muck. I'm not having it. We are going to get our apostrophes correct. There's only one Bayes. He was the Reverend Bayes. You can Google him if you like. And he gave his name to this form of analysis. Bayes' theorem. There he is, not Bayes' theorem. Okay. I'm going to write out probability of B in a slightly different way now. There's A and there's B. I'm going to rewrite this. I'm going to rewrite probability of B. Why am I going to do it? It sounds a bit abstract at the first. I'll stop in a few minutes. It sounds a little bit abstract at the first. It's because when we start to apply this theorem, when we start to apply it to trying to learn about the world, we'll see that this denominator here is problematic. So I'm just going to observe that has got two components. I'm going to say it's the probability of B given A times the probability of A plus the probability of B given A bar times the probability of A bar. Okay? Probability of B is two components. I should have written them in different colours. I'll do that. I'll write it in different colours. I'll write them in different colours and then you can see what's going on more clearly. Okay? Now I'm not going to prove this, but it's kind of obvious. This probability of B here has got two bits of probability which are disjoint. It's got this bit in the middle in blue, which is that, the probability of B given A, which is in there, times the probability of A, plus the red bit, which still got a bit of blue in it, which is the probability of B given A bar times the probability of A bar, which is the probability of being in there given that you're not in A. So you've got two components to your probability of B. Again, I could prove that if I wanted, but it's not interesting. It's not illuminating or clever. So now I'm in a position to rewrite Bayes' theorem. And again, it looks arbitrary and pointless, and all I'm doing is mucking around with circles and A's and B's and things. We'll see how we can use it to deduce all sorts of interesting things. Probability of A given B equals, I'm going to use this expression here, but I'm going to rewrite the probability of B. And you'll see why I've done it. It looks a bit forced at this stage, but when I change, all I'm going to do is change the symbols to another symbol, and you'll see exactly why I've done it. Sometimes I'll write prob, and sometimes I'll write P. We'll see why we've done that in a minute. I want you to observe at this point that on the left-hand side, I've got A given B. I've got A on the left-hand, I've got A, probabilities of A, with some condition. And on the right-hand side, I've got probabilities of B with some condition. I've flipped round from considering A and B. And I'm using, over and over again, I'm using the very simple facts of set theory about A intersect B equal B intersect A and so forth. Very, very straightforward. Why am I doing all this? I mean, this just seems to me like the most pointless piece of nonsense ever. You will see when I do this. I have got A and B. I'm going to just make this statement here. I'm going to write, instead of a pointy symbol with a pointy bit on the top, I'm just going to write two horizontal like a rugby goalpost. And instead of that, I'm going to write that. Anybody got a problem with this? Has anybody got a problem with the two lumpy bits on the right turning into one bit here? It's no problem. At some point, you're going to run screaming out of the room because you'll say, help, it doesn't make sense. Has anybody got a problem with me referring to this sticky bit with a lumpy bit on the right-hand side as data, which is observations? And we've been talking about this. We've been talking about Gaussian variables. We've been talking about p-values and so forth. Hypothesis. Has anybody got a problem with me naming A as H? Let me rewrite Bayes' theorem. So a hypothesis is a hypothesis which is a scientific statement about the world. So a hypothesis might be the world is less than 6,000 years old. As a hypothesis, it might not be true, but it's a hypothesis. Another hypothesis might be salt in diet leads to hypertension. Another example of a hypothesis might be that the probability of success in some trial equals 0.525. And I'm sure you can continue in this process here. We could have any number of different hypotheses that we like, and all sorts of different types of data. The data might be something like the temperature in Australia is 25 degrees centigrade at a particular place at a particular time. Data can be anything, any observation that you make. Now here's the killer. We've got some data, and we're wondering which observations that can account for that data. These are all different types of hypotheses. Let's have a nice clear and nice clean example here. Hypothesis is that the person is male, And the data is that the person has a beard. And of course, you know, if you've got a beard, it's going to be a bloke, isn't it? But what I'm going to do is analyze that using... Well, we'll come to that. What I'm going to do now is to rewrite Bayes' theorem with H's and D's, and then we'll put the interpretation on it, okay? And again, you won't be particularly perturbed by this, but when I give you other examples of the hypothesis, other examples of Bayes' theorem in use, hopefully you'll be horrified. So what's the probability that a person is male given that they've got a beard? In this case, the way that we think about it is that this causes this to be the case. All right? But what we're doing is going backwards. We're going to, because the person being male doesn't always cause them to have a beard. Some guys here do. But one thing's for sure, that females don't have beards, or not very often anyway. We'll put a small correction in there and see what happens. If we're talking about somebody at some kind of, maybe a pantomime or something like that with makeup on. Or a person apparently has a beard, maybe. You see, and all I've done is put that for that and that for that. I've just changed my A to my H. Now, the crucial thing is here that we can identify all these terms here on the right-hand side, and we can get something that we're interested in, which is the probability that our data set is actually telling us that this person is male. All right? Let's just have a look at that. What's this one? Probability of a D given H. So H is that the person is male. What percentage of men have beards? 20%? 10%? 10%. Where's that 0.5 from? Because half the population are male. Because that's just the same as that one. Now it starts to get interesting. What's the probability that you have your data given that the person is female? Well, let's just say it's 0 for the moment, times 0.5. 1. Straightforward and obvious and clear and clean. Until I start to change the assumptions a little bit. Until I start to change the assumptions a little bit, I'm going to now suppose we are backstage at a pantomime. Okay? If you're backstage at a pantomime, there's people wearing makeup and all sorts of peculiar things going on. What that means is that now probability of D given H bar, which is the probability that a person's got a beard given that they're female, now you're backstage and you're saying, right, let's have a look at all the girls here. What percentage of them, what probability is there of having a beard if you are female? And if you're in a pantomime, it might be something like 0.01. So it's rare, but possible. Let's say. You with me? Now, let's go through Bayes' theorem. Write it out all again. Probability of your hypothesis given your data, probability of male given that you're a beard, equals, just go through it, 0.1 times 0.5 over 0.1 times 0.5 plus, and now we've got this new conditional probability, probability of beard given female is now 0.1 because we're in a peculiar situation at a pantomime. All right? Multiply top and bottom by 0.5. Multiply top and bottom by 10. Before it was 1. In the normal world, if you see somebody with a beard, they are male. Not because only men have beards, because women don't have beards. So if somebody did have a beard, you'd know they were men. But now we're in this peculiar position of having pantomime dames who are female but with the makeup on. All right? So you go through it. It's still 0.9 because what you're doing is you're seeing all the people with beards and you're wondering how many are men and they've got a beard anyway, and how many are pantomime dames who are female but with a beard. And it turns out, according to this formula here, that most of them have got beards because they're male. 90% of the ones with beards are male, and 10% of them are pantomime dames with makeup on. I'm going to stop for a few minutes now and have a break. But we have turned around H given D. Here it's D given H. These are easy to evaluate. These are interesting, but impossible to evaluate without Bayes' theorem. Okay, I'm going to stop there for 10 minutes, and we'll reconvene at 10 past 10 according to that clock there. And I'll give you some more interesting and perhaps scientifically useful examples of Bayes' theorem.